In this video, I'm going to talk about pH, buffers, and the common ion effect. So the common ion effect is actually something you've seen before in chapter 14 when we were talking about equilibrium and Le Chatelier's principle. So the common ion effect is a shift in the position of an equilibrium caused by the addition of an ion involved in the reaction. So that should sound very similar to Le Chatelier's principle. So if we have an example, H2CO3, carbonic acid, producing H plus and HCO3 minus, which is bicarbonate. And if we add sodium bicarbonate to that reaction, the sodium bicarbonate breaks up into sodium plus and carbonate or bicarbonate minus. So notice that that is a product of the reaction above. So by adding more HC3O minus to the reaction, what does that do to it? It will shift the reaction back towards the reactants. So the presence of bicarbonate would shift the carbonic acid equilibrium to the left, and it decreases the ionization of carbonic acid, which means that we have fewer products, right? That makes sense. Add a product, reaction shifts to the reactants, thereby the H2CO3 would ionize less than it would otherwise. So let's just go through a quick example, and we're going to compare the pH of 0.1 molar acetic acid on this slide with 0.1 molar acetic acid in the presence of sodium acetate in the next slide. So this is just like a weak acid problem. We have 0.1 molar acetic acid initially present and no reactants. And then filling out the ice table, we're going to lose some of the acetic acid, we're going to gain some H plus, and we're going to gain some acetate ion. So in the end, our equilibrium line is going to have 0.1 minus X for the acetic acid and X for both our H plus and the acetate ion. Now, if we put all this into the equilibrium expression and solve for pH, remember, since Ka is small, we can ignore that X, making the math a little bit easier. And when we find the pH, it ends up being 2.87. Now, before we go on to the next slide, I just want you to think about what would happen if we added more acetate ion. So we add more acetate ion, where does the reaction shift? It shifts to the left, making more acetic acid. And if it makes more acetic acid, what happens to the concentration of H plus? And by extension, what happens to the pH? So what would you expect to happen to the pH if we added sodium acetate to this reaction? Just take a second to think about that before we go on to the next slide. Okay, so in this slide, we've added 0.5 moles of sodium acetate to the reaction, and we're going to set up the ice table in a very similar fashion as we did previously, except the difference here is we don't start with 0 acetate. We're going to start with 0.05 molar acetate because we've added 0.05 moles of sodium acetate, right? And sodium acetate ionizes to produce 1 mole of sodium and 1 mole of acetate. So the concentration of sodium acetate is going to be the same as the concentration of acetate. Now our equilibrium line is going to look a little bit different because right here we have 0.05 plus X, right? And that X is the same as this one on the left here. So if we could ignore this X, because the amount that this is going to ionize is so small that it's not going to affect the concentration of the acetic acid. So we're essentially left with 0.1 molar acetic acid, even after we've lost some of it due to this equilibrium. If we can ignore that, then we could also ignore how much is added to the concentration of acetate. Again, because the concentration of X is going to be so small that it's not going to affect the amount of acetate in that reaction. So we're going to ignore this X down here in our equilibrium expression as usual, but we're also going to ignore this plus X as well. Again, that makes the math a lot more simple. And if we determine the pH of this solution, we end up getting 4.44. So you can see that the pH is a lot higher than it was when we only had acetic acid in solution. And if you think about it, it makes sense because since the acetic acid is not ionizing as much as it would have if it was just by itself, right? The addition of the acetate ion forces that reaction towards the reactants. It reduces the amount of products, which means it would reduce the amount of H plus in this reaction. Right? So we reduce the amount of H plus. If we reduce the amount of H plus, then we're going to have a higher pH. So when you're thinking about the common ion effect, just think about Le Chatelier's principle, because that's essentially what it is. It's just an application of it. And when you're going through these ice tables, just make sure that you add the appropriate concentrations to the products, which is usually what will be added in this type of a question. So now let's take a look at pH buffers. Now, a buffer is a solution that is composed of a weak acid or a base and its conjugate partner, and they're both at reasonably high concentrations. Okay, so we're going to have HA in solution, and we're also going to have A- in solution. Now, you realize that if you only had HA in solution, of course it's going to make some of the A-. It's going to make some of the conjugate base on its own because it ionizes, it's in equilibrium with its conjugate base. But that's not a buffer. A buffer is when you have reasonably high concentrations of both HA and A-. If you just let HA ionize by itself, you know it doesn't ionize that much, so it's not going to create a lot of A-. So you'd have to add some of that conjugate base to the solution. Okay, so you would have, say, 0.1 moles per liter of HA and 0.1 moles per liter of A-. Okay, you're going to have approximately equal amounts of these in solution in order for it to be a buffer. There can be a little bit of a difference, and we'll get into that a little bit later. But for now, think of the concentration of HA and the concentration of A- being almost at equal concentrations. And the point of a buffer is that it is there to resist changes in pH. So if you have a buffer solution and add to it some strong acid or strong base, the pH isn't going to change all that much. Okay, so the point of a buffer is to resist changes in pH. The weak acid in this equilibrium is going to react with any added base by the reaction right here. And the weak base is going to react with any added acid through this reaction here. Okay, so those are just parts of this reaction above here. Okay, so one is the equilibrium of the HA making A-, and the other is the equilibrium of the A- making the HA. So the way to deal with these buffer problems when you're trying to determine a pH is to use something called the Henderson-Hasselbalch equation. And basically what it is, it's a rearrangement of this equation right here. What we're doing is we're rearranging this equation, solving it for the concentration of H3O+, and then taking the negative log of both sides. Right? So the negative log of the concentration of H3O+ is pH. And if we rearrange the equation, we'll have Ka on the right side of the equation, and the negative log of Ka is pKa, and then we're going to have the log of the remaining weak acid and conjugate base in that equation. Okay, so the Henderson-Hasselbalch equation, pH equals the pKa of the acid plus the log of the concentration of the base divided by the log of the concentration of the acid. And this is an easy way to determine the pH of a buffer solution. So here's a quick diagram to show you what happens when we have a buffer solution. So right in the middle, this bar graph right here, we have equal amounts of both acetic acid in red and acetate ion in blue. Okay, so that's a buffer with equal concentrations of conjugate base and acid. Now, if we add some OH-, some strong base to this buffer, what's going to happen is that strong base is going to react with the weak acid and convert some of it into the weak base. Okay, so the weak base is going to increase in concentration. The weak acid is going to decrease in concentration, but the ratio isn't going to change all that much. And if the ratio doesn't change all that much, then it turns out the pH also doesn't change that much. Now, if we add some strong acid to the same buffer, that acid is going to react with the base and convert some of that base into its conjugate acid. So in this case, we would have an increase in the concentration of the acid, a decrease in the concentration of the base, but again, the ratio of the concentrations of acid to base isn't changing all that much. So what happens again is the pH overall doesn't change all that much. I'm just going to go back to the previous slide to show you what I mean about that ratio. So the ratio I mean is right here, the base over the acid. Okay, so if that ratio doesn't change much, this part of the equation isn't going to change all that much. And if that part of the equation doesn't change much, then the pH overall isn't going to change very much. So let's just go through a quick calculation to determine the pH of a buffer solution. So calculate the pH of a solution containing 0.22 molar acetic acid and 0.13 molar sodium acetate. Ka of acetic acid equals 1.8 times 10 to the minus 5. So since we know this is a buffer solution, we know we're going to be using the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation requires the pKa, and we're given the Ka. So the first thing we're going to have to do is figure out what the pKa is. And that should be pretty simple. So the pKa equals the negative log of the Ka. So in this case, the pKa equals 4.74. And we have the rest of the information to solve this question. We have the concentration of acetic acid, so that's the concentration of HA. We have the concentration of sodium acetate, that's the concentration of A-. So all we have to do now is plug in those numbers into the Henderson-Hasselbalch equation, and we can figure out what the pH of the buffer is. So here's the Henderson-Hasselbalch equation, plugging in the pKa that we figured out from the previous slide, putting in the concentrations of the weak acid and the weak base, we end up getting a pH of 4.51. So how can we tell if our answer makes sense? So I want you to think about this equation a little bit. So we have a pKa of 4.74. What would this part of the equation be if we had equal concentrations of acid and base? If they were, say, both 0.13 molar? Well, it turns out that would end up being 0, right? So the log of 1 is 0. So if we had equal concentrations, the pH would equal the pKa. So you can think of the pKa as kind of the starting point for where the pH will be. It is going to be somewhere around the pKa if it's a buffer. So in this example, we have more acid than we do base. So we would expect the pH to be less than the pKa. It's on the acidic side of the pKa because there is more acid. If there were more base, then the pH would be larger than the pKa. So it's a good idea to check that when you're doing these calculations. You can make a prediction to determine whether you think the pH should be less than, equal to, or above the pKa, and then when you do the calculation, see if your prediction matches what you actually get. So let's talk a little bit about buffer range and capacity. So buffers aren't good over infinite pH ranges. Okay, so they're only good within plus or minus 1 from the pKa of the acid. So in the previous example, the pKa was 4.74. So to make a buffer with acetic acid and sodium acetate, it would be good over the range of 3.74 to 5.74. So plus or minus 1 from the pKa value. If the pH ends up being outside of that range, then it is no longer a good buffer, and we'll see why a little bit later. Buffer capacity is affected by the concentration of the buffer. So how much weak acid and how much weak base is the buffer composed of? The more weak acid and base that is in the buffer solution, the more strong acid and strong base it can deal with, right? There's more moles of weak acid, more moles of weak base, so it can handle the addition of more moles of strong acid or more moles of strong base. So buffers that have the greatest buffering capacity will have both high concentrations of weak acid and base, and they will be within the range of plus or minus 1 from the pKa. The closer to the pKa, the better the buffering capacity, because it can deal with both the addition of acid and base equally the closer it is to the pKa. But as long as the buffer is plus or minus 1 from the pKa of the weak acid in the buffer, then it's a good buffer. So this graph shows you how the pH would change after the addition of strong acid or base given different concentrations of the buffer. So we have a buffer concentration of 1 molar on the right-hand side of the graph, 0.01 molar on the left-hand side of the graph, and the pH change is given on the y-axis here. So if we have a 1 molar concentration of buffer, the addition of acid or base is not going to change the pH all that much. Okay, so the pH right along this dashed line here means that it's not going to change. That's the initial pH of the buffer. Now, as we decrease the concentration of buffer, you can see that the deviation from the original pH changes more drastically. So if we have 0.1 molar, we add the same amount of acid or base as we did up here, we notice you get a much larger change in the pH. And if you have a 0.01 molar concentration of buffer, then we have a very large change in the pH of the buffer. So this is just showing you that high concentration buffers have higher buffering capacities. You could add more acid or base to a buffer that has a higher concentration, and that will resist the pH better than if you add the same amount of acid or base to a lower concentration of buffer. So I've kind of already mentioned this, but it's worth repeating. Okay, buffers must satisfy a specific condition in order to be a good buffer. So previously it was worded like this. The pH has to equal the pKa of the acid plus or minus 1. So if the pKa was 5, then the buffer is good over the pH range of 4 to 6. Another way to write that would be this way here, is that the concentrations of the conjugate acid to the weak base must be within a factor of 10 from each other. So let's just see how this relates to this here by using the Henderson-Hasselbalch equation over on the right here. So we'll just add some different ratios to the equation. So in the first case, we'll have 1/10 ratio, so 10 times more acid than there is base. And what is the log of 1/10? The log of 1/10 ends up being -1. Okay, so there's the -1 in the pH equals pKa plus or minus 1. Now if we reverse this and we use a ratio of 10 to 1, so 10 times more base than there is acid, the log of 10 is +1. So that is the plus in the pKa plus or minus 1. Okay, so as long as the acid and the base are within a factor of 10 from each other, then it's going to be a good buffer because it satisfies this criteria here at the bottom, pH equals pKa plus or minus 1. And this table on the right just shows you some different pKa values for some different weak acids. So we have hydrofluoric acid, nitrous acid, acetic acid, and so on. And you can see that they have different pKa values, so they will be good for buffering at different pHs. So for example, HF will be good for a pH range of 2.15 to 4.15. HCN will be good for a pH of 8.31 to 10.31. So now let's go through a question of how to choose a specific acid or acid-base combination to prepare a buffer at a specific pH. So the question asks to select an appropriate acid and describe how you prepare a buffer with a pH of 4.5. And we're going to use the same table as we did on the previous slide. So since we're going to be preparing a buffer at pH 4.5, we need to choose one of the weak acids that has a pKa within plus or minus 1 from 4.5. And it turns out that there are 3 possible acids we can use, and those are indicated on this slide. Okay, so I'm going to use benzoic acid, so that's this one right here. Okay, you could use any one of them, acetic acid, benzoic acid, or formic acid. And since we're trying to determine how we're going to prepare this, we know what pH we want. We know the pKa of the acid that we're choosing. And all we're going to do now is we're going to solve for this ratio. So what is the ratio of benzoic acid to sodium benzoate, or benzoate ion, that we're going to need in our solution in order to make a pH of 4.5? So that ends up being 2.04. And basically what that means is that we're going to need about 2 times more benzoate ion, or sodium benzoate, because it's going to be in the form of a salt. So we need about 2 times more of sodium benzoate than we do of benzoic acid. So how would we prepare this in the lab? Well, we could dissolve 2.04 moles of sodium benzoate. That will give us the moles of this guy on the numerator of our fraction, and then 1 mole of benzoic acid, right? So that's going to give us a ratio of 2.04 to 1, and then dissolve that in 1 liter of water. Okay, and that'll give us a buffer that is approximately pH 4.5. Now, in real life, what you calculate using the Henderson-Hasselbalch equation isn't necessarily going to get you the pH that you actually thought you would get. Because when you calculate a pH, we're using concentrations, and it turns out that concentrations are actually an estimate of what's really happening with the chemistry of any solution. Okay, so the pH is governed by something that is called an activity, and this is nothing that we're going to learn about right now, and you may learn about this in later courses, maybe a third year PChem course. But just know that when you do the calculation, it's really an estimate. So if you were to actually take 2.04 moles of sodium benzoate and 1 mole of benzoic acid, you probably wouldn't get exactly pH 4.5. You might have to adjust it a little bit more. So instead of doing this calculation, how would you actually really do this in the lab? So here's what you would do in real life if you wanted to prepare the same buffer that we just did the calculation for. So you need 1 liter of a pH 4.5 benzoate buffer and at a concentration of 0.1 molar. So the first thing you're going to do is weigh out 0.1 moles of sodium benzoate and dissolve that in a beaker of about 800 milliliters of water. And then we're going to use a pH probe to monitor the pH as we're adding HCl to the reaction. So why are we adding HCl? Well, the HCl is reacting with the benzoate, right? The H plus is reacting with the benzoate and it's producing the benzoic acid. So instead of adding benzoic acid separately, we can just use a strong acid to convert some of the weak base into its conjugate acid. Okay, so we'll just keep monitoring the pH until we get a pH of 4.5, and then we're going to transfer this into a volumetric flask, dilute this to volume, so we will have 1 liter of a buffer at the appropriate pH and at the appropriate concentration as well. So that's about all I have for this section, and as usual, if you have any questions, please feel free to ask.